chapter, we're going to be discussing everything about compounds, so mainly their naming. We're going to learn how to name binary, covalent compounds, ionic compounds, acids, and then we're going to talk a little bit about the mole, how to find percent composition, empirical formulas, molecular formulas, and lastly, combustional analysis. So what are chemical symbols and formula, right? You might have seen things like this in your chemistry class. So these are basically chemical formula. So what do they mean? So each and every element has its own unique formula, right? And where do we get that naming? We get it from IUPAC, which is basically the International Union of Pure and Applied Chemistry. So every single symbol, sometimes made up to 2 letters. You can also have single letters like potassium. So each one of them denotes a certain element. Now, if you have a 2-letter symbol, your first is going to be capital, whereas your second is going to be small. It's extremely important to do that because let me show you an example. So when I say CO and CO, this is carbon dioxide, carbon monoxide, whereas this is cobalt. So that is very important. It's very important that if you have an element, the second letter should be small. Now, an element is your smallest, your element cannot be broken down further, right? Okay. Then we talk about chemical symbols and things like that, and how do you combine them? Common chemical symbols. So we have nitrogen, we have sodium, we have chlorine, blah, blah, blah. You can pause the video at this time and try to work out and see what are the name of these common chemical symbols. Now, where do we find these symbols? We find it in the periodic table, right? So this is the periodic table. We have about 118 elements, and this is where you would see your symbols. So this is your carbon, this is nitrogen, oxygen, lithium, sodium, hydrogen, right? Helium, fluorine, chlorine, bromine, things like that. So how do you name compounds, right? When I say CO2, what does this mean? How does this naming come up? How do you know this is carbon dioxide? So there is a convention. So when I have a formula like this, firstly, you need to understand what it means. It means that I have 1 carbon. So if you have just 1, you're not going to write a subscript. If you have more than 1, then you're going to include a subscript. So here you have 1 atom of carbon and 2 atoms of oxygen. Now, when you want to name covalent compounds, right, the first one, the first non-metal, is going to be named as it is. So say in CO2, it just stays as carbon. But if you have a prefix more than 1, you're going to add it. For the second one, you're going to add an IDE. Let me show you. So if I have a binary covalent compound, the first non-metal prefix is used only and only if it's more than 1. Always keep carbon dioxide in your head. So always keep the CO2 in your head. So because carbon is 1, we do not use a prefix. And the second guy, because it's more than 1, and even if it was just 1, for the second one, you will use a prefix regardless. Even if it's 1 or more, there will always be a prefix. What are these prefixes, by the way? So in chemistry, we have prefixes for saying 1, 2, 3, 4, 5. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, and 5 is penta, so on and so forth. These are the first 5 are the most important and the most commonly used. So you have to add the prefix plus the root. So here for CO2, the root is ox, the prefix is di, and then you add IDE. So that's how it becomes carbon dioxide. So let's look at another example. We have N2O. So the first the first symbol is named as it is, but because I have two nitrogen, so I will say dinitrogen. The second one is monoxide. There you have it. That's how you name a binary covalent compound. Some of them have exceptions and more common names, like H2O is just water, ammonia is NH3, and CH4 is called methane. So their names are more commonly and widely accepted. Then we talk about naming ionic compounds, right? When you name ionic compounds, you always have to first write the name of the metal. So your metal comes first, and then you have your non-metal, and usually the non-metal ends in IDE. If you have an oxygen present, the non-metal will either end in ate or ITE, and I'll show you those. So this is how you name an ionic compound, right? So let's see. So the first is that if I have a cation, and obviously you have your cation, that is your metal, constant charge. Now what does this mean? So which means if I do not have a transition metal, so this is group metals, right? If I have a constant charge. And variable charges is when you have transition metals. So if you remember, transition metals can have variable oxidation states, which means what? Like copper. Copper can be Cu+, copper can also be Cu2+, right? Then we can also have stuff like cobalt. Cobalt can be, or actually more commonly, iron. Let's talk about iron. So iron, so Fe2+ or Fe3+, right? So they have variable oxidation states. So you have to specify which one you're talking about, which is why they're saying you have to specify it in Roman numerals. So the name as it is, if it's a group metal, just the name. If it's a transition metal, you also have to add the numeral. Now the anion part of it, if it's monoatomic, that means if it's like chlorine or bromine or whatever, if it's single atom, then it's the root. So if it's chlorine, for example, it will be chlor, and then you add IDE, so it will make it chloride. So always remember sodium chloride, remember? So sodium chloride, you can keep that in your head. There are no prefixes used for ionic compounds. You have no prefixes for ionic compounds. That means the di, tri, tetra does not apply to ionic compounds. Okay, let's look at examples here. So if I have calcium chloride, right? So calcium is a group metal. It's in group 2. So I'm just going to write calcium. Chlorine is a monoatomic ion, so chloride. So it's calcium chloride. Whereas if you look at this example right here, I have iron and sulfate. So these are your polyatomic ions, right? Polyatomic ions. You need to know their charges and their names. Okay, so I have iron and sulfate. Now iron, remember I said, can have variable charges. It can be Fe2+ and Fe3+. So here what changes is I write iron and I specify the valency in the brackets. So this is 2. This is a Roman numeral 2. And then I write sulfate. So this is how you would name ionic compounds. Next, we want to talk about how do you name a hydrate. So for hydrates, for example, if you had something like this. So the naming is the same. So hydrates are also ionic compounds, right? But it's just that they're hydrated. They have water present in their molecules. So the first part you will name exactly according to the ionic naming convention. So this will be copper. I will specify the state. So this is 2. Copper, sulfate, Then what you do is you take care of this part of your hydrates. How many hydrates do I have? So I have 5, right? So I use the prefix. So I say pentahydrate. And that's it. So you have the first part, which is as normal as an ionic compound, and the second part you just show how many water molecules are bonded. So not bonded, actually absorbed into the compound. So this is pentahydrate. Next, we want to talk about how to name acids. So how can we name different acids, right? So if you have a binary acid, and that's exactly what we're going to look at in this lecture. So if you have a binary acid, the first is just going to be hydrogen, right? So you have H, and that is hydro. The monoatomic ion, you add the root. So say if it was HCl, this will be chlor. And you say ic acid, right? So let's see the example. So here I have chloride, right? So this is hydrochloric acid. It will be the same for HBr. So it will be hydrobromic acid, right? If I had, say, H2S, it would be hydrosulfuric acid. And that's it. But you also have exceptions here, right? So if you have other acids that you need to know names of. So we have HNO3. So this is called nitric acid. And then you have H2SO4. This is sulfuric acid. There's also sulfurous acid when you have H2SO3. And then you have H3PO4, which is phosphoric acid. So these are the most common ones that you need to know. So this is where you have it. This is what I wanted to show you. Anion has 8, so like sulfate, right? Then your acid will be sulfuric acid, what I showed you, which is essentially H2SO4, right? But if it has ite suffix on it, so which is like sulfite, then it would become sulfurous acid. Yep. But if it ends in ide, IDE, as normal, like chloride or bromide, then you just have something like hydrochloric, and the hydro prefix is added. So hydrochloric acid. So you can pause the video at this time and you can try to work out what is the chemical formula for the following compounds. These are the answers. All right, let's move on. The next thing we want to talk about is moles. This is very important. So what is molar mass and how do we find it? So let's think about the periodic table, right? So this is where you would find your molar mass. Say you have sodium somewhere around here. Yeah? So sodium has 2 numbers that you would see. So you would see 11 and you would see something around 22. Now, the atomic mass is what you would use to find the molar mass. So for sodium, for instance, that is just 22. Then for oxygen, so somewhere around here, if I were to talk about oxygen, you would see 2 numbers, which is 8 and 15.999. So if I were to find the molar mass of oxygen, it would be 15.999. But the only thing different for oxygen is that oxygen exists as O2. So I would have to do 15.99 times 2, right? So that will give me something around 32. So this is how you find molar masses of elements. And then we take the same approach and we find the molar mass of compounds. Compound like H2O. And I have to find the molar mass of this. So what do? So I say, okay, there are how many hydrogens? There are 2 hydrogens. And how many oxygen? 1. So I would say 1.008 times 2 plus 15.99 something. So you get your answer around 18 grams per mole, right? So this is your molar mass. And that's exactly how you can calculate molar masses for any sort of compound. Now, remember, when you have something like this, when you have coefficients, so if I had, let's say, for example, I have sodium hydroxide plus H2SO4 giving you sodium sulfate plus water, right? And when you balance this out, this would be 2, right? And if I had to calculate the molar mass of sodium hydroxide, what do? So I'm just going to say sodium is about 23, I believe. Plus oxygen, which is going to be 16 plus 1, right? And I just find the final answer. I am not going to account for this 2. This 2 has nothing to do with your molar mass. It's not going to be accounted for because this is just the coefficient. This is there for balancing. It's the number of moles you would need to react with H2SO4 to produce sodium sulfate. So please do not do that mistake. Next, we want to talk about how you find the mole. So mole is essentially the mass over your molar mass. This is the essence of stoichiometry. You cannot do stoichiometry if you don't know how to find the mole. So let's look at an example. So we have find the number of moles of 39 grams of aluminium chloride gas. And so first of all, mostly the formula would be given to you, but this you can write the formula, right? Remember, so we have Al and Cl. Do you remember swap and drop? So Al is essentially 3 plus, Cl is minus. So this is going to be 3 and 1. I swap and I drop and I get AlCl3. So I know that this is AlCl3. I can find its molar mass, right? So what is the molar mass going to be of AlCl3? So let's pull up the periodic table and we're going to quickly look at it. So you can open up your periodic table and you would notice that chlorine has a mass of 35.45, whereas aluminium is 26.982. So aluminium is 26.982 plus 35.453, right? But do I have only one chlorine? No, I don't. I have about 3 of them, right? So I'm gonna account for all of them. So if you quickly work this out on your calculator, you would get something around 133.341 grams per mole. Now I'm going to find the mole. So I'm going to say the mole equals 39 grams divided by 133.341 grams per mole. So this is going to come up to 0.292 moles. There you have it. You found the number of moles. Next, we want to discuss about percent composition. So percent composition is basically how you find the percentage of a certain element in a compound, right? And if you remember the law of conservation of mass and Dalton's law, you know that the percent of any of the element in a compound would always remain constant because they combine in fixed ratios, right? So the formula is essentially total mass of the element over total mass of the compound times 100. So let's see, how do we do it? So here we have an example, right? So we have how many grams of copper are in 20 grams of copper sulfate, right? So how do you work this out? First thing you need to do is so next we're going to talk about percent composition, which is essentially the total mass of the element in the compound over the total mass of the compound times 100%. So let's see a question. Suppose it says how many grams of copper are in 20 grams of copper sulfate pentahydrate. So how are you going to do this? So first of all, you need to find the molar mass of your compound. So let's look how we can find the molar mass of copper sulfate. So because this is a hydrate, you also have to take into account the water molecules. So you're going to take your molar mass of copper plus sulfur plus oxygen plus, so whenever with hydrates, I always take it as 18. So that's the molar mass of water. I think it's 18. 0.15 or 0.015, something like that. And then that is going to give you a value of, just give me a second. So this is going to come up to 250, sorry. So this is going to come up to 250 grams per mole. So now this is your molar mass. You have to find how much copper is in 20 grams. So what do? So you take your mass of copper, so percent composition is basically your element over your total molar mass. So that's going to be 63.55, which is your molar mass of copper, over your total molar mass, which is 250, times 100. So when you compute that, that is going to come up to about So this is going to come up to about 25.42%. So how much of it is in 20 grams? You're going to say 25.42 divided by 100 into 20. So that is going to give you about 5.084 grams. So this is the amount of copper you have in copper sulfate pentahydrate. Next, we're going to discuss about empirical formula. So how do you determine the empirical formula? So the first thing you're going to do is you're going to assume you have 100 grams of the compound. So if you have 100 grams of the compound, it means that you can convert these percentages to grams. So it becomes 143.7 grams of phosphorus and 56.3 grams of oxygen. And then you're just going to quickly divide by their molar masses to find the number of moles. So this is going to be divided by 30.974. You divide this by 15.99, so you get about 1.411 moles of phosphorus, and this is 3.519 moles of oxygen. Now the next step is that you divide by the lowest number of moles. So if this is 1.411 and this is 3.519, 1.411 is obviously the lower one. So you will end up with something as P1 and O as 2.49. Now obviously you cannot have half numbers, right? You need to have integers. You're looking for whole numbers. So you will multiply unless you get an integer. So if you multiply by 2, you will get P2O5. And that's it. That is your empirical formula. Next, we want to talk about how to find molecular formulas, right? So in molecular formulas, you will always be given the molar mass. That's very important to understand that. Okay, so let's read this question. It says 72.33 grams of a sample contains 28.9 grams of carbon, 4.86 grams of hydrogen, and 38.57 grams of oxygen, right? So what do you do first? You need to first find the number of moles. So let's find the number of moles of carbon, hydrogen, and oxygen. So this is going to be 28.90 grams divided by 12.011. So that comes up to about 2.406 moles. This is 4.86 grams divided by 1.008. And that gives me about 4.82 moles. For oxygen, it's 38.57 divided by 15.99, and that comes up to about 2.411. So you have your number of moles sorted, right? You want to find the molar empirical formula. So you have 2.406, it's just 4.82, O is 2.411. You divide everything by 2.406, and you will end up with this value, which is CH2O. Yeah? Now, this is your empirical formula, but you are looking for the molecular formula. So what do? You need to find what is called the multiplying factor. So multiplying factor is basically you divide your molecular formula mass by your empirical formula mass. So this thing that you found, CH2O, you need to find its molecular mass. So that's going to come up to about 30.026 grams per mole. So what do? You divide your molecular formula, which is 60.05 divided by 30.0026. That gives you 2. So when you multiply 2 by your empirical formula, which is CH2O, you end up with C2H4O2. And this is your final answer. So the next thing we're going to discuss is combustional analysis. So you have 2.5 grams of this particular compound. It yields 6.10 grams of CO2 and 2.50 grams of H2O. So the first thing you're going to do is you're going to find the number of moles of CO2 and H2O, right? So let's do that first. So we're going to find the number of moles of CO2, which is 6.10 grams divided by 44.009. Now, where do I get this 44? It's basically 1 carbon, 2 oxygen. So I end up with 0.1386 moles. Then I find the number of moles of H2O. So this is 2.50 grams divided by 18.015 grams per mole. So this also comes up to 0.138 moles. Now, you need to think about the amount of carbon and oxygen. So if I were to split this carbon with CO2, if I split the CO2, I will get 1 carbon and 2 oxygens, right? If you were to think about monatomic elements. So the ratio is 1:1, right? Let's think about this as monatomic so you understand what I'm trying to say better. But if I were to split the water, I will get 2 hydrogen and 1 oxygen, right? So you basically need 2 hydrogen atoms to form 1 molecule of water, whereas you only need 1 molecule of carbon to form 1 molar of carbon dioxide, which means if I have to find the amount of carbon, the number of moles of carbon, it's going to be the same for this guy. But for hydrogen, I have to multiply this by 2. So it's going to be 0.138 by 2. Okay. Now the next part is you want to find... All right, so the next thing is you're going to find the mass of carbon and the mass of hydrogen, So what is the mass of carbon? It's going to be 0.1386 times 12.011 that equals 1.66 grams. But for the mass of hydrogen, it is 0.1387 times 2, because remember we said you have to multiply it by 2. And then obviously into 1.008, and that gives you about 0.279 grams. Yeah? So this will let us find the mass of oxygen, which is just going to be 2.50 grams minus 1.66 plus 0.279 grams. Why? Because the compound contains carbon, hydrogen, and oxygen. So if I know how much carbon, if I know how much hydrogen, I can find the amount of oxygen. So that is 0.56 grams. So after that, it's just going to be the same. So you say CHO, I take my number of, I take my mass and I find the number of moles first. So this is going to be 12.011. This is 0.280 divided by 1.008. This is 0.56 divided by 15.99. So that is going to give me, for the CHO, I end up with the moles, which is 0.138. This is 0.278. And this is 0.035. So I divide by the lowest number of moles, which is obviously 0.035. And I get a ratio, which is going to give me C4H8O. But this is my empirical formula, right? I am looking for the molecular formula. So I need to find the multiplying factor again. So when I find the multiplying factor, how? I need to find the formula mass for this. So it's 12 times 4 plus 8 times 1 plus 16. So that comes up to about 72. So this is empirical formula mass is 72.106. Okay, so how do I find the multiplying factor? You take the molecular mass. Where do I find this? Go back to the question, this here. So the molecular mass is always going to be given. So 142.21 divided by 72.106, which is essentially the empirical formula mass, you get a 2. This 2 gets multiplied with this. So you end up with C8H16O2. And there you have it.